Hello and welcome to my new lecture. In this lecture, I am going to talk about molar specific heat of an ideal gas. This is topic 19.8 of the Fundamentals of Physics book by Halliday, Resnick and Walker. In this lecture, I would be talking about the internal energy of an ideal gas along with the molar specific heat at constant volume and molar specific heat at constant pressure of an ideal gas. Then I would be looking at the relationship between the degrees of freedom and molar specific heats. So let's start our discussion with internal energy. We have previously discussed specific heat at constant volume and pressure, but that was not the case of an ideal gas. In this lecture, we will be discussing all these quantities with respect to the ideal gas. Now first look at internal energy of an ideal gas. Now in discussing internal energy, I would first say that I am looking forward to derive the expression for the internal energy of a monoatomic gas like helium, neon or argon. I am taking monoatomic gas because it has a single atom and the monoatomic gas has only translational kinetic energy, whereas diatomic and polyatomic gases have not only translational kinetic energy but they also have rotational kinetic energy. So keeping these things in mind and the discussion from our previous section, we know that internal energy E of internal to be equal to 3 by 2 kT, where K is Boltzmann constant, K is Boltzmann's constant, and this T is temperature. We are considering this internal energy to be at the atomic level and not at a molecular level. So we know that the number of moles is equals to number of moles times the Avogadro's number give us the number of atoms, that is equals to capital N. So the internal energy for n moles of a gas would be equals to 3 by 2 n into Na times k into T. Doing a bit of mathematics, we know that K is gas constant over Na and K into Na would be equals to R. So I can write this internal energy to be equal to 3 by 2 nRT. This is another expression for internal energy of the atoms of an ideal gas. Let me call this as, this is my equation A and this is my equation B. One thing is clear from equation A and equation B, that internal energy of the system or of an ideal gas or atoms of an ideal gas depends only on temperature. It doesn't depend upon any other variable. I think some of you might have lost the vision of the page as the camera was not there. I can explain it again, that internal energy for n moles should be equals to n into Na. I have substituted it over here. Then I have done a bit of mathematics, that K is equals to R over Na. That internal energy comes equals to 3 by 2 nRT. And these two equations show that basically internal energy depends only on temperature and it doesn't depend upon any other variable. As we have calculated this internal energy of an ideal gas moles or molecules, then we would be able to calculate the molar specific heat at constant volume and at constant pressure. Let's first look at the molar specific heat at constant volume. Constant volume means the volume does not change, and this molar specific heat is represented by Cv. C sub of V is molar specific heat at constant volume. Now consider that n moles of a monoatomic gas are confined in a box like this, and it has been kept at constant volume. So this piston cannot move up or down in this case, and this is thermal reservoir from where the heat can enter the system. Now I would like to explain this situation with the help of a PV diagram. I am taking the volume to be along x-axis and pressure along y-axis, and suppose that my monoatomic gas initial state is at this point, and the pressure at this point is P and the volume at this point is V, and temperature at this point is T. Now if I add the heat to the system, its temperature will increase, and let's say this is my final state, and you can see that the volume remains constant in this case. This straight line shows that there is no change in volume, but obviously the temperature has increased. Let me call this change as T plus delta T, and the pressure has changed. Let me call this as P plus delta P. Now the volume has remained constant and the pressure has changed from P to P plus delta P, and this change would be delta P, and the temperature has changed from T to T plus delta T. Now according to my given situation, I can write down the amount of heat energy to be Q to be equals to NCV delta T, using the concept of the previous chapter that Q is equals to NC delta T, that is molar specific heat. In this case, since the molar specific heat is at constant volume, so I have put Cv over here. Now according to first law of thermodynamics, the change in internal energy is equals to Q minus W. If I substitute the value of Q over here, then E internal would be equals to Q is NCV delta T. Now the work done in this case would be 0 since there is no change volume as we are taking the case of a constant volume process. So W would be equals to 0 and this gives me CV to be equals to change in internal energy per unit and delta T. I can name these equations. This is my equation C, this is, let's say, my equation D, this is my equation E, and this is my equation F. Now for internal energy delta E internal, I have to keep this equation B in mind, that internal energy is 3 by 2 nRT. When I would take delta E internal, it would be delta T, since all other quantities are not dependent upon change. So I can write from equation B I know that delta E internal is equals to 3 by 2 nR delta T. Substituting this value of delta E internal into equation F would result in CV is equals to 3 by 2 R. This is my molar specific heat at constant volume. However, one thing should be kept in mind, that this is for monoatomic gases only. For the this is for monoatomic gases. For diatomic gases, this CV is equals to 5 by 2R. And for polyatomic gases, this CV is actually equals to 3R for polyatomic gases. There is a table 19.2 in your book where the molar specific heat at constant volume for monoatomic, diatomic and polyatomic gases have been given. Now if I substitute this molar specific heat at constant volume for monoatomic gas in this equation E, substituting this value would result in internal energy for a monoatomic ideal gas to be equals to N into 3 by 2 R times delta T. This would be equal to 3 by 2 nR delta T. This is my equation G, and this gives me internal energy of a monoatomic ideal gas at constant volume. This expression gives me the internal energy or change in internal energy of a monoatomic ideal gas. I think we have reached to this equation B as a result. This equation G and equation B are same. Now from equation B, I again, if I write it down from equation B, internal energy is equals to 3 by 2 nR delta T, and I can substitute 3 by 2 R to be equals to CV, then this would be equals to N CV delta T. This is my equation H. So this equation H is actually my general expression for the internal energy of an ideal gas at constant volume. I can use the value of CV for monatomic, diatomic or polyatomic gases and then find out the internal energy at constant volume. Once again, you can see that the internal energy of a confined ideal gas depends upon the change in temperature only. It only depends upon the change in temperature. It does not depend upon the what type of process produces the change in the temperature. To explain this result, you can see that this internal energy only depends upon this delta T, change in temperature. It does not depend upon which process has produced this change from the initial to the final temperature, final stage. It could be heat added to the system or anything else. Only variable of concern for internal energy of an ideal gas at constant volume is change in temperature. In next part of our discussion, I would be looking at molar specific heat at constant pressure. Molar specific heat at constant pressure. To consider molar specific heat at constant pressure, I again consider the gas molecules confined in a container like this, and there is a piston that can move up or down, and here is a thermal reservoir from where I can add the heat to the system. In this case, the volume can be increased. Now let's look this diagram in terms of a PV explanation. This is volume, this is pressure. Let's say this is initially this is temperature and this is my initial point, and the pressure at this point is P, and let's say the volume is V. Now this system undergoes a change from initial to final state. If we add heat to the system, its temperature will increase. There would be an increase in volume as the piston will move upward, and let's say the system reaches some final stage like this, and this is my final state. As I have kept the volume of this pressure of this constant, so there is no change in pressure, one can see that. However, there is a change in volume, and let me call this as this change as delta V, and this would be V plus delta V. This point would be V plus delta V, and this change in volume is delta V, and the change in temperature is T plus delta T. This delta T is change in temperature, and this delta V is change in volume. From our previous discussion, we know that the area under the curve in this case is, let's say, P times delta V, and we would see later on that it appears as work, as P is area under the curve of a PV diagram, or work done is equals to P times V. Here in this case it would be P times delta V, which we would see later on. Now the amount of heat that is added is equals to Q is equals to n moles of an monoatomic gas, since it is at constant pressure Cp times delta T. This is my amount of heat. Now from first law of thermodynamics we know that internal energy is equals to Q minus W. Now I have to substitute different internal change in internal energy, amount of heat, and the value of this work done. The internal energy from equation H we know that is equals to NCV delta T from H, equation H, and Q I have already written it, and now I have given it a name as equation I. Q we know that is NCP delta T, and as I told earlier that work done is equals to P delta V, right? We have in our previous chapter we know that work done is equals to P dV. On the similar step for a monatomic n gas moles, it should be equals to P times delta V. Now substituting all these values into the equation of first law of thermodynamics, what I get is this change in internal energy is equals to NCV delta T is equals to Q is equals to NCP delta T, and this work done is P delta V, and by ideal gas law we know that it can be written PV is equals to nRT, so it could be written as nR delta T. So I would substitute it as nR delta T. Now doing a bit of mathematics, dividing it by n delta T would result in CV is equals to Cp minus R, or you can say that molar specific heat at constant pressure is equals to molar specific heat at constant volume plus ideal gas constant. Now you can see that this molar specific heat at constant pressure is large as compared to molar specific heat at constant volume, just as molar specific heat at constant pressure was equals to 3 times the molar specific heat at constant volume. You might remember the relationship beta is equals to 3 alpha in case of expansions at constant pressure and at constant volume. As you can see over here that that Cp is greater than Cv. This prediction of molar specific heat at constant pressure and constant volume is not only for monoatomic gases but also for other gases, as long as our assumption of ideal gas that density remains small is valid. In the second section, I would start the discussion about degrees of freedom and molar specific heat. In previous section, we took the molar specific heat at constant volume Cv is equals to 3 over 2 R, and this was true for only the gas with a monatomic gas. This result is not exactly valid for diatomic or polyatomic gas molecules. one of the reason is that for monatomic gas molecules we have only translational kinetic energy, and by quantum theory we do not include rotational kinetic energy for monatomic gas molecules. However, diatomic and polyatomic gas molecules have rotational kinetic energy as well, so this same expression cannot be held true for those cases. To explain this these motion, I have taken a monoatomic gas molecule of helium. Then I have taken a diatomic gas molecule of oxygen, and then I have taken a polyatomic gas molecule of methane, CH4. And we are assuming in this case that all these three types of molecules, monoatomic, diatomic and polyatomic, have translational motion, means they can move along x, y or z direction, and the diatomic and polyatomic have rotational motion as well. They can move around their axis. These molecules can move around their axis, and these diatomic and polyatomic have oscillatory motion as well. They can move towards or away from each other, whereas this monoatomic has only the translational motion. It can move right, left or up or down. To keep track of the various ways in which energy can be stored in a gas, James Clerk Maxwell introduced the theorem known as equipartition of energy. And what this theorem states: every kind of molecule has a certain number f of degrees of freedom, which are independent ways in which molecules can store energy. Each molecule has 1 by 2 kT per molecule, or 1 by 2 RT per mole energy associated with it. So each molecule has 1 by 2 kT per molecule and 1 by 2 RT per mole of energy associated with it. Now to explain this, first we consider translational motion. Since in case of translational motion, each molecule or each mole of a gas can move along x, y or z direction, so it has got 3 degrees of freedom. So we can write it down as 3 into 1 by 2 kT. This would be the energy associated with translational motion. This would be for per molecule and for 1 by 2 RT per mole. This is for case of translational motion. For the case of rotational motion, each molecule can be considered with its center on axis, and it can move in 3 directions, x, y and z. It can rotate along 3 directions. So the degrees of freedom in this case would be 3 into 1 by 2 kT per molecule. However, one thing should be considered in mind, that this rotational motion having degree 3 as degree of freedom is only true for polyatomic gas molecules. Since we already know that monoatomic gas molecules do not have rotational motion, and for diatomic gas molecules we have only 2 degrees of freedom. For diatomic, this is for polyatomic, and for diatomic we have 2 degrees of freedom, so it would be 2 into 1 by 2 kT per molecule. The diatomic gas has 2 degrees of freedom because you can see over here that it can rotate along this only. It cannot move along the line joining these molecules. So it can rotate from top to bottom in this case, and not from between right to left. It cannot rotate from right to left. So that's why it has got 2 degrees of freedom, which is not the case for polyatomic gas molecules. So we need to rewrite our case of internal energy that we wrote down as internal energy to be equals to 3 by 2 nRT. To include the degrees of freedom F, we can write this internal energy to be equals to F by 2 nRT. Now generally speaking, this CV would be equals to F by 2 R by comparing the equations of internal energy with our previous results. And this F is equals to 3 for translational motion only, and for rotational motion this F is equals to 5, and for monoatomic gas molecules this is for monoatomic. I should explain it rather than writing it down. This F is equals to 3 is for monoatomic, and F is equals to 5 is for diatomic, and F is equals to 6 is for polyatomic gas molecules. I would like to rewrite this value of F is equals to 3 for monoatomic gas molecules, F is equals to 5 for 5 degrees of freedom for diatomic, and F is equals to 6 for polyatomic gas molecules. Now after having a discussion about molar specific heat for ideal gas and how to calculate degrees of freedom for monoatomic, diatomic and polyatomic gas molecules, let's do some numericals related with these topics. So the first numerical is numerical number 42 of the book, which is stated as: what is the internal energy of 1 mole of an ideal gas at 273 Kelvin? We should know the formula for internal energy of an ideal gas, and it is given by 3 by 2 kT, right? Or you can use delta E internal equal to 3 by 2 nRT. The number of moles of an ideal gas are given as 1, temperature is 273 Kelvin, and the value of R is equals to 8.31 joule per mole per Kelvin. You can substitute these values in this equation and find out the internal energy of this ideal gas. I am leaving these calculations to you people. You can use your calculator and solve this expression for internal energy of an ideal gas. Second numerical related with today's discussion is numerical number 51, which is stated as when 1 mole of oxygen O2 gas is heated at constant pressure starting at 0 degree centigrade, how much energy must be added to the gas as heat to double its volume? And the hint is given: molecules rotate but do not oscillate. The question looks a bit tricky at the start, as we know that Q is equals to NCP delta T, and right now we only know that N is equals to 1 mole in this case. We do not know about Cp, and we would calculate delta T. Now let's first look at Cv. Cv in terms of degrees of freedom is equal to F by 2 R, as we have just noticed it, which is 4.16 F, and it has been given that molecules can only rotate but do not oscillate. So it has got degree of freedom F is equals to 5. For diatomic gas molecules it would be 4.16 into 5, which comes out to be 20.8. Now Cp would be equals to Cv plus R, which would be 20.8 plus 8.31. This would be 29.1. Now substituting all these results, Q would be equals to N is given as 1, Cp is 29.1, and delta T is 0 degree centigrade or 273 Kelvin. So when you will multiply these values, you will get the amount of heat energy that is required in this case. So this sums up our discussion related with the molar specific heats for an ideal gas, in which we looked at the internal energy of an ideal gas and then internal energy of an ideal gas at constant volume and then at constant pressure. Later on, to include the motion of rotation as well as oscillation, we move to the topic of degrees of freedom and molar specific heat, in which we found that the monoatomic gas molecules have only translational motion, while the diatomic have translational as well as rotational motion, and polyatomic gas molecules have translational as well as rotational as well as oscillatory motion. And then later we found out how you can calculate Cv, means molar specific heat at constant volume, in terms of degrees of freedom number, which is given by F. And then at the end of this lecture, I have solved two numericals, one related with the internal energy of an ideal gas and the other one related with the degrees of freedom of an ideal gas. Hopefully you understand this lecture. I would be back soon with a new lecture. Thank you all for your time.